to at the time or something like that. And then there's a fourth category we've been working on lately, which is human rights activists. For them, they like the privacy properties, but really it's about reachability. It's about, I can't get to CNN right now, and with something like Tor now I can. Or I can't read my local blogs because all of my local blogs are censored. Or I can't get to my blog, so I can't post on it because my government is trying to prevent me from doing that sort of thing. So part of the goal of Tor is to take all these different groups and put them into the same network so that they can blend together. You can't have the cancer survivors anonymity system, because if the only people who are using it are people who had cancer and are talking about it, then everybody knows why you're using the anonymity system. So the goal here is to have a lot of different groups out there, so if you see somebody using Tor, you can't conclude, aha, I know why he's using Tor. So how do you build one of these? The easy answer is that single hop proxy I was talking about before. So we've got these various Alices, and they each send all their traffic to the middle relay, and the relay goes out and gets it. So the first problem is, what if that big central point of failure fails? There are so many different ways that maybe you can subpoena them, you can go look at the single cable that goes into their computer and comes out, and you can tap it. You can send a guy named Guido on an airplane to go gently ask them for all of their data. You can bribe the CEO, here's $50,000. Maybe they'll give up the data. They don't really care. It's not their data anyway. So that's one failure mode. A worse failure mode is, don't pay any attention to the relay itself. Just look at all of these connections going into the relay and the same connections going out. It's one cable that goes into the computer and another cable that comes out. And then just do the traffic analysis and start saying which of these flows coming in matches up to which of these flows going out. And that math is surprisingly easy, and it's getting easier as the years go by. So we want something where there is no single cable, there's no relay, there's no central point that gets to learn which users are talking to which destination. So the idea there is to distribute the trust over multiple hops. So Alice is going to pick a path through several relays, and no single relay gets to learn which Alice is talking to which Bob. So if R1 is bad, if R1 is trying to figure out who's talking to who, he knows Alice is using Tor because he sees Alice talking, but he doesn't know what she's doing. He can't figure out what's going on the Bob end. And if R3 is bad, if he's trying to figure out who's talking to Bob, he knows somebody's talking to Bob, but he doesn't know who. And if R1 and R3 are collaborating, then we're screwed. So the security that Tor gives us, as the network gets larger and larger and we have a more diverse set of relays, then there are fewer and fewer attackers who are big enough, who are in the right place to be able to beat it. And then there's crypto, but I'm not going to talk about the crypto today. So that's our crash course on Tor. So far, so good? How many people here are Tor users? How many people here use Tor at least once a week? Perfect. Okay. Okay, so let's think a little bit more about this circumvention side, this censorship side. How do you build a tool that prevents people from blocking connections into Tor? One of the big challenges we had a few years ago was Tor provides good anonymity, but if governments can prevent people from reaching the Tor network, if they can block all these connections from Alice to the purple boxes, then it doesn't matter how good Tor is. If people can't reach the Tor network, then it's only for people in countries that are still willing to let people reach it. So let's think a little bit more about how to build one of these circumvention tools. The first thing to think about, there are two pieces to all of these proxying schemes. The first piece is what we call the relay component. How do you actually build your path? How do you get the encryption right? All that stuff I was talking about on the previous slides. And then the second piece is the discovery component. How do you learn what the relays are? How do you learn who you can connect to out there? And in the case of Tor, we have a really simple discovery component. There's a centralized directory. There are these 7 directory servers. I run one. The 2 people down there each run one. I think there's another person in here who runs one. So there are 7 people around the world that we all trust, and they never get into a single location at any given time. And as long as a majority of those 7 are good, are safe, are not lying to you, then they will produce a big list of all the relays, and it will be the right list. It'll be the same list that everybody else gets. So the way this works is all of these relays over here publish what's called a self-signed descriptor. They publish a little summary. Here's my IP address, exit policies, keys, stuff like that. And they send all of that to the 7 trusted directories, and then those authorities talk to each other and they produce a signed consensus saying, here are all the relays, their addresses, the timestamps you should expect to see from them, that sort of thing. And then that multiply signed consensus gets cached on all the other relays and Alice fetches it. So it's a very simple discovery component. There's a directory, it lists all the relays, you get it, you're done. Now you know what the Tor network looks like. And that's great for most situations. It provides better anonymity properties than some other designs, but it's pretty straightforward to block. So how can attackers like the Chinese firewall block connections into the Tor network? So the first answer is there are those 7 authorities that I was talking about. And if you get their IP addresses, they're hard-coded in the Tor software, you block all 7, now nobody can bootstrap. The second approach is you pull down that list of 1,500 relays and you block all of them. China did that at the end of September. A third approach is you filter your traffic based on looking at the network fingerprint. You say, Tor is going to make a request, it's going to look like this on the wire, I can do TCP dump or something fancier and recognize that request, and then I'm going to hang up on that sort of thing. And an American company called SmartFilter and another American company called WebSense, back in 2007 or 2006 or something like that, they came up with a signature for how to recognize Tor traffic. And then they sold their software to Iran, UAE, Sudan, the list goes on. And that was how those countries were able to block connections to the Tor network. So that was back in 2007, and that's what got us all going here. We were thinking, I don't mind if Wikipedia, for example, wants to decide which Tor users are allowed to edit Wikipedia, but I do mind if countries are starting to say, you're not allowed to reach the Tor network, you're not allowed to have privacy, you're not allowed to decide for yourself what on the internet you're allowed to read. So that third approach was done for a little while in 2007, and then we fixed Tor so it was a lot harder to recognize the fingerprint. We made it look like SSL. And then there's the fourth approach. If you block torproject.org, then a lot of people who used to be using Tor now say, well, that was nice. Tor used to work, now it doesn't. And Tor still works. The network's still reachable, the software still works, but you can't get to the website, so you figure it's all shut down. So these are 4 different approaches that different countries have been using. So the approach that one of the approaches we've been using to solve this is what we call bridge relays. So we've got these purple relays over here. There's a big list of 1,500 of them. But we've got a few 100,000 users. We've got a whole lot of people over here. And what if we give them another button that says, I want to help censored users. I want to be a relay, not in the public list, not something that can easily be blocked, but I want to be a dark relay, a private relay, what we call a bridge relay. And the idea is you can bridge from somebody inside a country that can't reach Tor to the bridge to the Tor network. And that means that these bridges don't have to be exit relays. They don't have to deal with legal hassles from police and so on. They're just passing traffic from Tor to Tor. And they don't have to pass very much. If you've got 20,000, 50,000 bridges and 20,000 or 50,000 users, then 10 kilobytes, 20 kilobytes a second is a lot. So all of you who raised your hand earlier and said, yeah, I use Tor every week or so, you should turn yourself into a bridge. You should be one of these people who are available for the folks in China and Iran and other countries so that they can get through you to the rest of the Tor network. Okay, so let's think a little bit more about what's actually happened over the past little while. Did I skip a slide? No, I didn't. Perfect. Okay. What's actually happened? Here is a graph of the number of people using Tor from Iran and from China in June. So right here is where the Iranian elections happened, And suddenly a whole lot of people in Iran were starting to say, I need to be able to reach external news sites in order to tell them what's going on in my country, and I need to reach Twitter, and I need to reach Facebook because there's some sort of action or demonstration happening tonight. Where is it? Who is it? I need to learn these things. And it got to the point that there were 8,000 or 10,000